Hello fellow viewers, my name is Moses and welcome to the Physics Show. In today's episode we will be constructing an AC generator and basically explaining the physics principles by which it operates. Now the main materials we'll need to do this are two strong magnets, at least two strong magnets, a pair of alligator clips, a cardboard box, a coil, and maybe a screwdriver just to be able to turn it as a handle. What you got to do is you've got a piece of cardboard, cut it and draw markings in order to bend it, make a perfect sort of little opening like that, little box to fit magnets in. So what we've done here is we've made a little box, sticky taped it, and we've just made a hole to put our nail in. So this is basically where the rotation will take place and the turning. The magnets will go in there. Okay, so now we're just turning the coil. We're putting the coil on it. We're making sure we're not actually hitting the screw and not pressing the cardboard. And we have to get about 300 turns to move the magnet slowly, which will be in here, and to basically turn on the light bulb. Yep. So basically after you've made at least 300 turns and able to have a hole in which you can place the main instrument we use for our rotation, I've placed a screwdriver in here so we can twist it. After this you'll basically need to grab at least one strong magnet and just place it inside there, and place another magnet, another strong magnet inside. So there you have it. So you're twisting that the magnets along with the screwdriver act as our rotor. However, the coil in this case acts as the stator. And what you basically need to do after you've attached these magnets inside, the last step you will need to do is basically solder the ends of the wire to this. Solder the ends of the wire to the clips, and you're basically ready to conduct electricity and test it out. So we have the multimeter here, and we can test it out. Just place each one correctly in there, and put on the right setting, and we test it, and we have successfully created an AC generator. As we can see, we are getting a reading, and this reading is basically determined, it's proportional to the strength that I put onto this, to the force I put onto this screwdriver or the rotor. So once I stop, it goes back to zero. Now the basic purpose of an AC generator is that it is a device that converts kinetic or mechanical energy into electrical energy. Furthermore, the main components of the AC generator are the rotor, as we have here, the magnets along with the screwdriver, create the magnetic field, and we have the stator, the stationary part of the AC generator. The moving parts of the generator are known as the rotor, and its rotations are due to the interaction between the windings, as we have here the screwdriver, and the magnetic field. We have here our magnetic field, which produces a torque around the rotor's axis. So we're producing a torque basically here, and gives us reading. Torque is produced here, a turning motion around the rotor's axis. The stationary parts of a generator are known as the stator. The stator may act as the field magnet, interact with the armature to create motion, or it may act as the armature, in this case, acting as the armature, receiving its influence from the moving field coils on the rotor. However, in this case, the coils are the stator, they are not moving, stationary. A generator also consists of a coil of wire, which the current flows. So here the current is flowing through the coiled wire straight into here, into the soldered part of the clips, which gives us the reading. Another part of the generator is the armature, which has two roles. The first is to carry current crossing the field, thus creating shaft torque in a rotating machine or force in a linear machine. The second role is to generate an electromotive force, EMF. Furthermore, the present-day generator runs on the principle of electromagnetic induction, shown by Michael Faraday in 1831 to 1832. Faraday discovered that the flow of electric charges or electrons may be induced by moving an electrical conductor, as in this case we are moving the screwdriver along with the magnetic field. This acts as our electrical conductor and our rotor, and it creates a flow of current via the electrical conductor, the wire in this case. Consequently, in generators, a current is generated from the spinning of the central armature, the torque. Here we have our central armature, and current flows through there. So that is the principle that we are following in order to make this generator. We follow the present day principle, and Faraday complied with this principle. Faraday discovered this principle. As directed from the syllabus, we may describe generated potential difference as the rate of change of magnetic flux through a circuit. The generated potential difference or voltage is equal in magnitude to the rate at which the magnetic flux through the circuit is changing with time. The equation derived to calculate the total generated potential difference is as follows: E equals minus delta phi B over delta T, where E is equal to the generated potential difference, and phi B is equal to magnetic flux density, and T equals time in seconds. So that is generated potential difference as the rate of change of magnetic flux through a circuit. Consequently, we are introduced to the concept of Lenz's law. When an EMF is generated by a change in magnetic flux according to Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it. The induced magnetic field inside any loop of wire always acts to keep the magnetic flux in the loop constant. In the examples below, if the B field is increasing, the induced field acts in opposition to it. If it is decreasing, the induced field acts in the direction of the applied field to try to keep it constant. Now, back EMF opposes the supply EMF. Due to Lenz's law and the result of a back EMF in the rotor within a generator, there must be energy conserved throughout the system. For this to occur, the back EMF that is induced must oppose or flow in the opposite direction of the supplied EMF that is being put into the system. The smaller the back EMF, the greater the current flowing through the coil. Now, how are eddy currents produced in terms of Lenz's law? Eddy currents are produced between the relative movement of a metal, not necessarily magnetic, and a magnetic field. So as we have here, relative metal and a magnetic field. There are small circular paths due to resistance. Eddy currents produce heat, and these currents produce a magnetic field that, due to Lenz's law, opposes the original changing magnetic field.